B trees. B trees are self-balancing trees. They are optimized for systems that read and write large blocks of data. They are good examples for external memory. They are used in databases and file systems. The definition of B tree is that a B tree of order M, if non-empty, is a M-way search tree. An M-way search tree means an M-way search tree are extensions of binary search trees. So M-way search trees are extensions of binary search trees. A binary search trees are trees in which a node, when we take a parent node, the nodes to the left of the parent node will have a value which is less than the parent node, and the nodes to the right of the parent node will have a value which is greater than the parent node. That is the concept of a binary search tree. So M-way search trees are extensions of binary search trees. That means it also satisfies this criteria. And in M-way search tree, the variable M, it shows an integer. It holds an integer value which is called the order of the tree. So here M-way search tree means it's of order M. Order M means each node of an M-way search tree can hold at most M branches. That is, it can hold up to a maximum of M branches and M-1 keys. That is, in each node of an M-way search tree can hold M-1 key values. Before, in BST, a node can hold only one. BST means binary search tree. Binary search tree, a node can hold only one key value. But in M-way search trees, the node can hold a maximum of M-1 key values and M branches. Now the definition of B tree. A B tree of order M, if non-empty, is a M-way search tree in which it should follow the following conditions. The first condition is that the root has at least 2 child nodes and at most M child nodes. That is, the root of a B tree of order M should have at least 2 child nodes and maximum of M child nodes. The internal nodes in a B tree except the root must have at least M/2 child nodes. So must have at least M/2 child nodes and maximum of M child nodes. Then the number of keys in each internal nodes is 1 less than the number of child nodes. That is, if a node has 5 child nodes, then the number of keys that node can hold is 5 minus 1, that is 4. Now the last one is all leaf nodes are on the same level. In a B tree, all the leaf nodes will be on the same level. Now look at an example of a B tree of order 5. This is an example of a B tree of order 5. Now you can see that the root node has a minimum of 2 child nodes, and the maximum child nodes that a node in B tree of order 5 is 5 child nodes. And if a node has 5 child nodes, that means it should have 4 key values. Now look at the last node. In this node, you can see that this node has 4 child nodes. That means it can hold a value of 3 keys. It can hold 3 keys in this node. So this is the representation of a B tree of order 5. Also, you can see that all the leaf nodes of this tree are on the same level. Okay, and the second point, that is the internal nodes except the root must have at least M/2 child nodes. That too ceiling of, that is, if the value of M is 5, then 5/2 should be rounded to the next value. That is, 5/2 will when it is rounded to the next value, it becomes 3. So the internal nodes except the root should have at least 3 child nodes for a B tree of order 5. Now look at the internal node. This is an internal node. It has 3 child nodes, and this is also an internal node which has 4 child nodes. So these are the conditions for a B tree of order M. Insertion in B tree. Now consider the given B tree of order 5. We'll insert the elements 4, 5, 58 and 6 in order so that we can see how the B tree is going to be self-balanced. How it will self-balance after insertion. Okay, let's start with the first element, that is 4. So since B tree is a search tree, we know that when we try to insert an element, we start from the root. Check the values in the root. Since here we have 3 key values, and the key values are arranged in ascending order so that it will be easy for us to search. So let's start from the first value. Take the element which we are going to insert, which is 4. Compare this 4 with the first key value. So while comparing, we can see that 4 is less than 8. That means 4 is to be inserted to the left of the key value 8. So look at the left node or the left subtree. Check whether you have space for insertion of 4. So in the left subtree, we can see that there is a node with 2 values, 2 and 7. So according to the conditions of a B tree of order M, we know that all internal nodes in a B tree, all the internal nodes except the root have at least m by 2 child nodes and at most m child nodes, right? So these conditions should also be followed after insertion. So we can see that the maximum number of child nodes that a node can have is m. That is, in this case, 5. Since the order is 5 here, so in this case, the maximum number of child nodes at this B tree can hold is 5, right? So, and if it can hold 5 child nodes, that means an internal node can store up to 5 minus 1 key values. Okay, so look at this node. Here we have just 2 key values. That means there is space to hold 2 more key values. So this 4 has to be inserted to the left of 8, which can be included in this particular node itself, because we can hold up to 4 key values in this node since it is of order m. So 4 will be inserted in the left node of 8. And it should be written in the ascending order so that it will be easy for searching. So after insertion of 4, we can see that the tree looks like this. That is, 2 is inserted to the left of 8. Since this node contained only 2 key values, one more, we can insert 4 easily into this without any adjustments or balancing. It is self-balanced here. So this is the result after inserting the element 4. Now the next element to be inserted is 5. So we will insert the 5 into this particular tree. Okay, now to insert 5, we'll start from the root itself. Now compare the first key value with the element to be inserted, that is 5. So comparing 5 and 8, we can see that 5 is again less than 8. That means 5 is to be inserted to the left of 8. So look at the left subtree of 8. Here we have only one node and it has 3 key values. Since the order of this B tree is 5, we can store up to 4 key values in a node. That means we can store one more key value in this node. So 5 will be inserted to the left of 8 and it will be included along with these values. That means the order will be 2, 4 and 5 will be in between this 4 and 7. if when we write it in ascending order. So 2, 4, 5, 7. This is how we will get. Now to insert 58. So starting from the root, we have to look where 58 is to be inserted, in which child node 58 is to be inserted. Now checking with the first key value of the root. Now 50, since 58 is greater than 8, we will go to the next key value. Now we can see that 58 is less than 96. That means 58 should be inserted to the subtree which is in between 8 and 96. So it will go to this particular node, and now 58 is to be inserted along with this node. That is, we have to find the exact location where 58 comes. That is, in the sorted order, we can see that 58 comes in between 55 and 86. So 58 will come here. That means 58 will come here. But now look at the number of keys in this node. You can see that there are 5 keys in this node if we insert 58 along with this. But since the Btree is of order 5, we know that the maximum number of key values at a Btree of order 5 is 4. So 58 cannot be included with this. That means for now we have to balance this tree. So for that, write the key values in the ascending order. Now the key values in the ascending order are 37, 46, 55, 58 and 86. Now select the value which is in the middle. Now when these values are in the ascending order, we can see that 55 comes in the middle of these 5 numbers. Now this 55 should be shifted to the parent node, Now look at the parent node. The parent node has 3 keys. A Btree of order 5 can hold up to 4 key values. That means this 55 can be accommodated in the parent node. So the parent node or the root node becomes 8, 55, 96, 116. So 4 key values will be included in the root, and these the child nodes. That is, if there are 4 key values in a node, then it should have 5 child nodes. That means this node will be split into 2 and it will be included here. Now the tree will look like this. Is how we get when 55 is shifted to the parent node and the child nodes will be split into 2 child nodes. And now you can see that the root node has 4 key values and the number of child nodes has become 5. This is the maximum number of child nodes that a Btree of order 5 can have. Now to insert 6 to this tree. Now compare 6 with the root value. So while comparing, you can see that 6 should be inserted to the left of 8. That means 6 should be included in this node. So while if we include 6 in this node, 6 will be between 5 and 7. That is, 6 should be inserted here. Now look at the number of keys in this node. It has become 5, which is not possible for order 5. So one key value should be lifted to the parent node. So after arranging it in the ascending order, we have to select the middle one. The middle one here is 5. That means 5 should be lifted to the or shifted to the parent node. So when we lift 5 to the parent node, this node will be split into 2. That is, one node will be containing the key values 2, 4 and the other one will be containing the key values 6 and 7. Now 5 will be included in the parent node. Now while writing it in the ascending order, 5 will be on the left of 8. Now look at the number of key values in the root node. Here it is 5, which is also not possible. That means we have to take the middle element we have to lift the middle element to middle element up. That means select the middle element. Here the middle element is 55. It should be shifted up. That means 55 now becomes the root, and this node now will be split. So 55 becomes a root, and 5 and 8 will become the left node, and 96 and 116 will become the right node, and all the others will be arranged in the next level. That is, the level has now increased by 1. So this is how the tree looks after lifting 55 to the root. So 55 has become the root, and 5 and 8 has become the left child of 55, 96 and 116 has become the right child, and all the other nodes have been arranged accordingly. Here 2, 4 and 6, 7 were split into 2, that is over here. The other one is shifted to in this way, and all the other nodes are arranged accordingly. So this is how insertion takes place in a B tree of order 5.